So welcome to the Lundbeck lecture course. So Anna Caraiani of Imperial College London is going to tell you the next four lectures about a glimpse into the Langlands program.
Right. Well, thank you. And yeah, it's really an honor and a pleasure to be here. And so, I want to give you some sense about what the Langlands program is, but without really sort of getting too technical maybe, or like, so this is supposed to be something like grand unified theory of mass that connects different areas, such as number theory, algebraic geometry, representation theory. And so compared to Charlotte, I guess I come more from the perspective of algebraic number theory and arithmetic geometry, whereas I guess in Charlotte's lecture course, you've seen the perspective coming from representation theory. But so from the point of view of number theory, it's connected to some of the oldest and deepest questions that you can ask about whole numbers, and it's also connected to some kind of very famous conjectures or theorems. So that's what I'm going to talk about today. And so just start out with a very basic question about whole numbers. What can be the last digit of a perfect square? So if you think about it, a perfect square can end in 0, 1, 4, 5, 6, 9, but it cannot end in 2 or 3 or 7 or 8. And you can ask this question not just about the last digit in base 10, but you can ask about the last digit in base given by any whole number. And using the Chinese remainder theorem, it turns out you can reduce this question to asking about what can the last digit of a perfect square be in base given by a prime number. And so this is the question that we're going to start with, is, so let L be a prime number. I'm going to take this to be at least 5. And so let's take one of the ones that didn't work in base 10. Can 3 be the last digit of a perfect square in base L? And so the answer, of course, depends on what the value of the prime number L is, but it turns out that you can understand it systematically. And one way to rephrase this that is more sort of even like kind of has a very number theoretic flavor is i.e. is 3 a quadratic residue? Modulo L. So modulo L means that we're going to ignore multiples of L. So that's why, if you're looking at the last digit in base L, you're forgetting all the other digits which correspond to multiples of L when you write out the number in that base. And yet another way to rephrase this question is, if you look at the polynomial x squared minus 3, when does this have a solution? Well, does it have a solution like if I look at x squared minus 3 equals 0 on itself? It doesn't have a whole number solution. But I can ask, can it be 0 up to multiples of L? When does this factor? As a product of two linear polynomials. And that's what it means, again, to have some number whose square up to multiples of L is equal to 3. Okay, and so the answer to this question is given by Gauss's law of quadratic reciprocity that goes back a few hundred years. And so this tells you that if you have two different odd prime numbers, P and L, here, and they're distinct. So I'm going to write this symbol maybe some of you have seen it before, P over L. So this is going to be +1 if P is a quadratic residue modulo L. So if P can be the last digit of a perfect square in base L. And I'm going to write -1 otherwise. So it's just +1 or -1. And the law of quadratic reciprocity tells you that this one times L over P, these are intricately tied together. So both of them are either +1 or -1, and their product is -1 to the Q -1 over 2 times L -1. I don't have a Q. P -1 over 2 times L -1 over 2. So this tells you that whether P is a quadratic residue modulo L is very intricately tied into whether L is a quadratic residue modulo P. And so, for example, if we take E to be equal to 3, and we look at this equation, what we get is that 3 is a quadratic residue modulo L, depending on what is, right? So this times L over 3 is equal to -1 to the L -1 over 2. And so this depends. Well, it depends on what L is modulo 3, because this is +1 or -1, depending on whether, say, L is 1 mod 3, then it's a quadratic residue. If it's 2 mod 3, it's -1, it's not a quadratic residue. And it also depends on what L is modulo 4. So it depends only on L modulo 3 times 4, so modulo 12. So in other words, this is something that maybe, you can't think of an answer right away if I give you a really big prime number like 1093 or 1637. But then if you use this law of quadratic reciprocity, then you can get the answer quite quickly, because all you have to do is see where that prime number falls on the 12-hour clock. So, you look at the 12-hour clock behind you. So for example, if I look at 13 or 37 or 1093, then all of these fall at 1. All of these are congruent to 1 modulo 12. And so that means, because of this law, it means that the answer must be the same for all of them. And then it's very easy to get the answer for 1093, because you just have to see that the answer is yes for 13. Why is that? So the answer here is yes. Because, for example, 16, if you write it in base 13, its last digit will be equal to 3. Okay, on the other hand, if you look at 17 or 29 or 1637, then all of these fall on the 12-hour clock at 5. And so then the answer for them will be the same as the answer for 5. And essentially, when we were thinking about the last digits of perfect squares in base 10, we already thought about what happens modulo 5. And we saw that really 3, so 3 or 8, are neither quadratic residues. So 3 is not a quadratic residue modulo 5, and here the answer is no. Right, so you don't have to square all the numbers up to half of 1637 and check whether the last digit could possibly be 3. You just use this reciprocity. And so I guess the Langlands program is about getting more and more sophisticated reciprocity laws, and they really end up not looking, well, one aspect of the Langlands program is about this, but they end up looking very, very far from this basic example. But I'm going to try to kind of lead you through towards what kind of the modern notion of reciprocity looks like. So we can ask a question. So to try to derive more reciprocity laws, in some sense, first we can ask, so how do we characterize the set of primes such that the quadratic polynomial x squared minus 3 splits as a product of distinct factors, right? So that's that interpretation of being a quadratic residue. Modulo L. Distinct, and I can put here linear. Okay. And so the law of quadratic reciprocity really tells you that, that say the number of distinct factors of x squared minus 3 really has to do with what L is modulo 12. So it's very easy to characterize as just periodic with period 12. But you can ask this for more sophisticated polynomials. And so one level up, so this is kind of example 0, I'm going to take you to the next level up of difficulty, where instead of a quadratic polynomial, we're going to look at a cubic polynomial. So we can look at x cubed minus x minus 1, right? And we want the same thing. Can we describe the set of primes L such that this, again, sort of splits as a product of distinct linear factors modulo L. And okay, so it turns out that really trying to give such a simple description, like, okay, here's like, it's the set of primes that satisfy this congruence, this is going to be hopeless for a cubic polynomial like this. So the way that we're going to characterize it is by giving a generating series. So there is so in this case, in here, we have a generating series. And I'll tell you what this is. So I just want to look at a power series in a variable q that you get by expanding a certain infinite product. So I define this as q times the product from 1 to infinity of 1 minus q to the n times 1 minus q to the 23n. And okay, so you want to expand this as a power series in q, and you can do this because for each power of q, you only have a finite number of terms contributing. And so I'm going to write this as a sum from n equals 1 to infinity of bn q to the n. And then it turns out that the number of factors, so I guess you can get the primes L such that this splits as a product of distinct linear factors by looking for the primes L for which the coefficient B sub L is equal to 2. So somehow there's a funny relationship between the number of solutions of this cubic equation modulo L and the coefficient of this power series. So I'll tell you the answer. The answer is that we're looking for primes L that are different from 23 and that have the property that the coefficient BL is equal to 2. As you expand this out, you'll actually see that the coefficients can really be, I think, -1 or 0 or 2. So you don't have that many choices. And then the primes modulo which this splits into a product of 3 distinct linear factors are the ones where the coefficient is precisely 2. Yeah.
I might have missed this, but where did the number 23 come from?
This is an example that you can work out more in the problem session. So I think in Alice's problem set, you can look at this example in a lot of detail. But one way to see it, this has to do with kind of primes of ramification. So like 23 is ramified in the, say, splitting field of this cubic polynomial. But yeah, so that's an excellent question of, how can we see 23 on this side? And it turns out you can recover it. And I'm not gonna kind of do this example in a lot of detail because it is in one of the problem sets. But what happens is that this generating series is really the Fourier expansion of a weight one modular form. And so if you know that you're looking for a weight one modular form, then kind of you can get information from this cubic polynomial to tell you where you should look for this form. So for instance, yeah, you can look at kind of the primes of ramification. And that's how you end up finding this. Right, but this is kind of, much more sophisticated than the first example. And it already uses to actually kind of prove in some rigorous way that, that's quite tough to do in this setting, just going from a quadratic to a cubic polynomial. It's much more subtle to see why these two things are connected. But that's another example of a reciprocity law where you are characterizing the primes where a certain polynomial splits into a product of distinct linear factors. Okay, so what I want to do now is move on to maybe an example that's even more sophisticated in some way. So instead of looking at polynomials in one variable, I want to look at cubic polynomials in two variables, and that's going to be the case where we start seeing elliptic curves. So example 0, we've had example 1, example 2 is we're going to look at what can we say about y squared plus y equals x cubed minus x squared. So what I've done is I've taken a cubic polynomial, but now there's two variables. And so because there's two variables, you don't really want to think about kind of breaking it up into, what you want to know is how many solutions does this have modulo L? And so how many, right? So how many solutions does this have modulo L? So how many pairs x and y of whole numbers can you write down, but whole numbers that are kind of just considered in their equivalence class, where they're equivalent if you change them by multiples of L. So how many such pairs can you find so that y squared plus y is really congruent modulo L to x cubed minus x squared? And unlike these first two examples, so here, you have up to 2 solutions. Here you have up to 3 solutions. Here the number of solutions grows with L. And so you're not just gonna, you may still be able to write down a generating series, but the number of solutions is kind of unbounded as L grows. So let's say that the number of solutions is n sub L. And so it turns out that in this case, you have a generating series that's kind of similar to this. This is again obtained by expanding out an infinite product. So this is Q product from 1 to infinity, 1 minus Q to the n squared, 1 minus Q to the 11n squared. Okay, so again, this gets expanded as a sum from 1 to infinity, an Q to the n, and then the kind of the reciprocity law, which I should really put in quotation marks because it really starts to resemble that less and less, is that the number of solutions and L is, well, differs from L by this coefficient. This is kind of the reciprocity law in this setting. So if you want to find the number of solutions to this equation modulo L, just have to expand this out and find the Lth Fourier coefficient, and then it's this difference, L minus AL. Okay, and I want to tell you what these mean. So first, this is something that you can sort of see and think, oh, this is a coincidence. Like it's an intriguing coincidence because you can pick a very large prime number and kind of compute this number of solutions there, and you can expand this out and check that this really matches up. But it still just feels like a coincidence, but it's not. It really fits into a very systematic framework. And this systematic framework is the modularity of rational elliptic curves. So let's see. Yeah, right. So y squared plus y equals x cubed minus x squared. This really kind of defines a curve. And if you projectivize this equation, it will give you a projective curve. And this is a so-called elliptic curve. So I'll say this is a rational elliptic curve. P over Q. So an elliptic curve is a smooth projective curve of genus 1. So if you think about this curve as a Riemann surface, it's a one-dimensional torus. And it also has a specified rational point. In our case, so we have this affine equation. When we projectivize it, we add a point at infinity. The point at infinity is the specified point. So this is kind of more in the language of number theory, where you write out a polynomial equation and you count solutions modulo primes. But you can translate this more into the language of arithmetic algebraic geometry, where you think about it as a curve and you think about the number of points that this curve has over a finite field. And one thing I wanted to say here, so again, you can parallel this question, where does 11 come from? So one exercise, if you know about, say, curves, is to convince yourself that if you look at this equation, modulo 11, this doesn't give you a smooth curve. So 11 is the one prime where this elliptic curve has bad reduction, actually. All the other primes, the reduction is still an elliptic curve. And then this NL is counting basically all the points on the elliptic curve except for the one at infinity. So if you wanted to add the one at infinity, it would be NL plus 1, and then you get L plus 1 minus AL. And I think there's another exercise on Alita's problem sets that will kind of explain where this comes from if you have a more sophisticated formulation of modularity. Okay, so that's on the side of number theory, arithmetic geometry. I also wrote down a generating series. So f of q, this infinite product, a power series that I got by expanding this infinite product, this is the Fourier expansion of a modular form. So a modular form, which I'll call f of z. And so this is a function on the upper half complex plane that has a lot of symmetries. And one of the symmetries is that it's symmetric under sort of translating z by 1. F of z plus 1 is equal to f of z. And so that means you can take a Fourier expansion. And our q, which was just a variable, a random variable before, is supposed to be this e to the 2 pi by z. So z is, a complex number with strictly positive imaginary part. And this is the Fourier expansion of it. And the reciprocity law is an instance of the modularity. So this relationship between NL and L minus AL, this is an instance of the modularity of rational elliptic curves. Okay, and so what I want to do now is talk more systematically about what modularity means. Feel free to interrupt with questions at any point.
There a big reason why 3 and 11 are both multiple of 12 minus 1.
I don't, yeah, it's hard to say. I mean, these are just some examples, but I could have chosen different examples. Okay, so as I said before, we have these kinds of two sides. So on one side, we have our elliptic curve, which is, it's an object in algebraic geometry because it's a curve. It's also an object of arithmetic algebraic geometry because the curve, the equation has coefficients over the rational numbers. And so that gives it extra symmetries. And on the other side, we have a modular form F, which is really an object in harmonic analysis. So this is a holomorphic function on H, so the upper half plane. And with lots of symmetries. In particular, this symmetry. F of z plus 1 equals f of z. And I'll tell you more about the symmetries in a second, but I want to talk about sort of how to connect these objects. And the way that you do it is through certain number theoretic objects that are called Galois representations. And right, so that uses the notion of representation from Charlotte's talk. And kind of the Galois has to do with the fact that we're looking at symmetries of algebraic numbers. So over here, I'm going to write the Galois group of the absolute Galois group of Q. So kind of the symmetries of all algebraic numbers. This is a profinite group. You can think of it as an inverse limit of the Galois groups of finite extensions of rational numbers. So it has this funny topology. It kind of looks like a Cantor set. And it turns out that both the elliptic curve and the modular form F give you a way to extract not sort of information about this Galois group through a certain representation of it. So from either side, you can construct a representation of this Galois group that's really a very big and complicated group. So I'm going to call this G sub Q. And then from E and F, we get two-dimensional representations of this Galois group. So they're representations on two-dimensional vector spaces. So they're given by 2 by 2 matrices. I guess like many of the matrices that showed up in Charlotte's talk. The vector spaces are over the field of p-adic numbers. So it's the p-adic completion of the rational numbers Q. And now the kind of the modularity can be expressed in a more sophisticated way as saying, well, we start out with the elliptic curve E, we construct a two-dimensional Galois representation, we start with the modular form F, we construct another one, and then the reciprocity law, the modularity is saying that they're isomorphic. So this is how the elliptic curve and the modular form are matched. Right, and so how do we construct rho E? I want to tell you a bit about how to get rho E, then a bit about how to get rho S. And then we have a kind of more sophisticated understanding for what modularity means. So rho E is constructed from the Tate module of the elliptic curve. Something called the Tate module. I'll just tell you what it is. It's actually very simple. So our elliptic curve is not just a curve, but it has a group structure. And when the elliptic curve is defined over the rational numbers, the group structure is also defined over the rational numbers. So if you think about it as a Riemann surface, so as a one-dimensional complex torus, your preferred point you can take as the origin, and then you can just imagine addition of points. But what's happening is because this is defined over the rational numbers, you can write down the group law. You can write down what it means to add coordinates in terms of polynomials that have rational coefficients. So polynomials in, say, x1, y1 and x2, y2. And so that means that if you're trying to find, say, torsion points, so points that, say, if I have some prime number p, I look at points that under multiplication by p get sent to the origin. If I try to do this, I end up writing down some polynomial equations in x and y. And so if I want to find the coordinates of those, I end up solving polynomial equations with rational coefficients. And so the solutions, the x and y that I get, they may not be rational themselves, but they're going to be algebraic numbers. And so for this reason, this is going to have an action of the absolute Galois group of Q. So it's going to have this Galois symmetry that comes from the fact that you can, the coordinates of the torsion points are given by algebraic numbers. So they have these Galois symmetries. And I can do this for p torsion points. I can also do it for p to the n torsion points for any integer, any positive integer n. And as n varies, this kind of gives you a compatible system of kind of Galois, of objects with Galois symmetries. And that's what the Tate module of the elliptic curve is. So this is how you get the Galois representation. You choose a prime number p, and then you kind of look at like very deep p to the n torsion points, and you look at the Galois symmetry of those, and that remembers something about the elliptic curve. So just abstractly, this looks like, well, if you think on the torus, a one-dimensional torus, what does it mean to look at the torsion points? They kind of look like a lattice that has two directions. So if I look at p to the n torsion points, they will look at like z mod p to the n z squared. So kind of two copies that are independent of z mod p to the n z. But then we're putting this Galois action here. And as you're letting n vary, you get the p-adic integers, zp. The field of p-adic numbers is just that, but with p inverted. So putting these together, right? And then QP is just CP with p inverted. Okay, so this is kind of a concrete way of constructing a Galois representation from this object of arithmetic algebraic geometry that was the elliptic curve that we started with. And if you're interested in computational things, you can imagine like really sort of finding the torsion points and trying to understand the Galois representation explicitly. But it turns out there's also a very kind of high-minded way of thinking about constructing this kind of Galois representation, which is to kind of, like hide it all under saying it's a machinery. And I think this also came up in Charlotte's talk. So there's this machinery that's called étale cohomology, that whenever you start out with an algebraic variety defined over a number field, will produce some Galois representations for that. So the same answer, essentially the same answer, will be given by looking at a certain cohomology theory for algebraic varieties. And this Étale cohomology, I guess, developed by Grothendieck more than 50 years ago, can be applied even to algebraic varieties that don't have this group structure and where you can't do things as explicitly as you do it here. So that's the next. So row F, we won't be able to do as explicitly. So this was constructed using this machinery. So from a certain kind of cohomology, cohomology, of something called modular curves. So let me try to unpack this for you a little bit. So it's some cohomology theory for algebraic varieties, say defined over Q, that will give you a vector space, but also equipped with an action of this very big and mysterious Galois group, the absolute Galois group of Q. So it's kind of like, if you haven't seen this before, don't worry about it. And I mean, in some sense, it's like, it's supposed to mirror like singular cohomology or, Betty cohomology for manifolds. But it somehow applies to algebraic varieties. And I think maybe Seeing might mention it in her problem session at some point. But you can also just take it as a big black box. But then what I don't want to take as a black box is what these modular curves are. So these are really the spaces on which modular forms live. So I said that a modular form is a holomorphic function on the upper half plane with many symmetries. So the upper half plane, you think about the complex plane. And so it's all, right, everything that you would find strictly above 0 on the imaginary axis. That's the upper half plane. But then this has symmetries under the group SL2Z. This is the group of 2 by 2 matrices with integer coefficients and with determinant 1. And so SL2 shows up again. Right, so how does this act on the upper half plane? If I have a matrix gamma of the form A, B, C, D, then gamma Z is AZ plus B over CZ plus D. Right, so if this is an SL2Z, then this is still, and so if this is this and Z is in the upper half plane, then it's an exercise to check that what you get is still in the upper half plane. And so, for example, you have the matrix 1, 1, 0, 1 that sends Z to Z plus 1. Or you have the matrix 0, 1, minus 1, 0, sends Z to minus 1 over Z. And SL2Z is actually generated by these two matrices. And so really the spaces on which modular forms live are not the upper half plane, but really the certain quotients of the upper half plane by the groups under which the modular form has symmetries. So if I want to picture what the quotient of H modulo the whole of SL2Z looks like, well, what I can do is I can look at I can look at the interval from -1 to 1, and because I have that first matrix in there, I can translate, right? And so what's happening is that it's not always necessarily true that the function is just constant when you apply one of these. But what's true is that the way that the modular form changes can be predicted. And so the function is just determined by the values that it takes in this interval. There's no point looking outside because you'll know, if you know it has this kind of symmetry, you'll know what it will look like outside this region here. And then if you think about what 0, 1, minus 1, 0 does, it's almost like an inversion about a circle, but also followed by a reflection. So I can do, sorry, someone should have interrupted me. I wanted to put 1/2 here. Thank you. So this is for this matrix. Right, so this region is for 1, 1, 0, 1. And then you can look at the unit circle. Here I have -1 and 1. And I can do this. So this is for the matrix 0, 1, -0. Okay. And again, sort of anything, like if I know what it looks like outside the circle, I can also figure out what it looks like inside of it. And so really the modular form is just determined by the values that it takes on this region here. Maybe I do this yellow. And so I want to look at just this region here. And that somehow, but including the boundary, that's where the modular form lives. And sort of naturally the quotient will be if I also identify the boundary. So I want to identify this piece with this piece, and I want to identify this piece with this piece. And then H mod SL2Z looks kind of like, you know, what happens when you take this region that can extend all the way to infinity in the imaginary axis, and you glue this boundary to this boundary, you kind of fold it. So what you end up getting is somehow like a punctured sphere, but that kind of towards this I infinity, you have this kind of cusp. So it looks something like this. And where this goes towards this, like I infinity would be the cusp over here. And otherwise it looks kind of like a Riemann sphere, maybe with some funny points that occur where kind of the boundary isn't smooth. So around I and around a cube root of unity. But so, okay. So when you want to think about modular forms, what you really want to think about first of all is, you know, where do they live? What does the space on which they naturally live look like? And in general, it will be something like this, or maybe a cover of it. So it depends on the precise group of symmetries that the modular form has. So our modular form S has symmetries under a certain congruent subgroup. So this is a subgroup inside SL2Z. So just 2 by 2 matrices with integer coefficients determinant 1. You can cut out a subgroup by imposing a congruence condition. Right here, I'm going to look at matrices that are of the form, so A, B, 11, C, D, with A, B, C, D. Well, anyway, how should I put it? Maybe I should have put it as gamma in SL2Z, such that gamma is congruent to. Point is that this entry in here has to be 0 at this modulo 11. So if you want, right, the condition is that if I look mod 11, then, you know, gamma's in the Borel, right? Upper triangular matrix. All right, and so this is a finite index subgroup in here. And so the space that I'm going to look at is not going to be this, it's going to be a cover of this. It's still going to be, because it's built by taking this kind of quotient of the upper half plane, it's going to be a Riemann surface, but it could have higher genus. So it's not necessarily a punctured Riemann sphere, but some cover of it, and it's not compact. It might have one cusp, it might have several cusps. I guess this one is going to have 2 cusps, so it might look something like this. That would be our H mod gamma 0, 11. Okay, and so what I want to do, maybe I don't have so much time today, but tomorrow I want to really go over in detail how to construct this Galois representation attached to a modular form. Because this is more subtle than in the case of the elliptic curve. You have to kind of reinterpret what a modular form is in several different ways, and you have to think about several kinds of different cohomology theories for these modular curves. I'll tell you the punchline, and then I'll repeat it tomorrow. So the really miraculous thing that happens here is that these are not just Riemann surfaces, but they're really cut out again by algebraic equations with coefficients in the rational numbers, or maybe with coefficients in some number field, some finite extension of the rational numbers. And so these modular curves already give you a link to arithmetic geometry. And then that's why we can think about their étale cohomology. So this is this, but the point is that there exists some x gamma 0, 11 that's maybe defined over a number field. Such that x gamma 0, 11 of C is this quotient. So there's a lot more structure in the spaces on which modular forms live on, and because of that, the modular forms themselves can be connected to arithmetic algebraic geometry, even though they originally start out in this world of analysis. Okay, so we'll talk more about, I think my plan tomorrow is to really go through how to go from certain modular forms, say the ones that are like our F, so the ones that are attached to elliptic curves, to Galois representations, and just give you some idea for how this is done. This is again something that goes back, I guess at this point, about 50 years, and it's due to Eichler, Shimura, and Deligne in this setting. And then, so after that, I want to really talk more about the geometry of modular curves. And in the last lecture, I want to talk about generalizations of modular curves. So higher dimensional algebraic varieties that still have a lot of these symmetries that modular curves have, and that are very useful in constructing and understanding the Langlands correspondence. But what I want to do today is end with discussing modularity. So I want to state a precise theorem, or maybe even mention a few results. So theorem, and this was pioneered by Wiles and Taylor Wiles in 1995. So for certain elliptic curves, so-called semi-stable elliptic curves, and then by Breuil, completed by Breuil, Conrad, Diamond, and Taylor in 2001. And this says the following: let E over Q be an elliptic curve. So as an approximation, you can think about it as this kind of cubic equation with in two variables. Or you can think of it as a smooth projective curve of genus 1, defined over the rational numbers. Then E is modular. So all such things have attached to them one of these highly symmetric objects called the modular form. So i.e., there exists a modular, and here there's a bit of a subtlety. It's not just a modular form, but a modular eigenform. So among modular forms, there are some special ones that are simultaneous eigenvectors for certain averaging operators called Hecke operators. So there exists a modular eigenform F such that the Galois representation attached to E, constructed from the Tate module of the elliptic curve at some prime P, is isomorphic to the Galois representation attached to the modular form F. So constructed from, say, the étale cohomology of a particular modular curve, and sort of that remembers kind of the system of eigenvalues attached to the modular form F. So these are just two-dimensional representations, and that they're isomorphic means that, so up to a change of basis, you can describe them in the same way with the same matrices up to conjugation by something that changes your basis. This can recover. So this recovers the explicit reciprocity law. L minus NL equals AL. So the one that we kind of discussed, first of all, as a very kind of concrete evidence that there are higher reciprocity laws, more sophisticated reciprocity laws out there. You can recover this by taking traces at so-called Frobenius elements from L, say for L ranging over all but finitely many problems. And what happens is you have your row E, and you evaluate it on an element or really on a conjugacy class, and you get a matrix up to conjugacy. Its trace is a well-defined element. And you can do the same thing for row F. And because the Galois representations are isomorphic, trace doesn't care about conjugacy, so these traces are equal. And then you can rewrite this as L minus NL, and you can rewrite this, or you can match this with A sub L. And so this is how you get the very explicit thing. And I guess in this case, for us, we're going to look at primes that are not equal to 11. It's the only one we have to exclude. So again, there's an exercise in Alice's problem set that kind of walks you through this, talks about what this Frobenius element is, and walks you through understanding this very explicit reciprocity law from this isomorphism of Galois representation. Okay, and I want to mention some consequences. I mean, in some sense, this was a theorem, or the consequence of this theorem is how I ended up being an algebraic number theorist, because when I was 13 years old, I read a book about the proof of Fermat's last theorem. So as many of you maybe know, this modularity of elliptic curves was the key step in the proof of Fermat's last theorem. And so that was some, big open problem for 300 years. So consequences of modularity. So it has applications, it has Diophantine applications. As this is called, is, when you look at equations and you try to find whole number solutions, and the famous application here was Fermat's last theorem. So the fact that x to the n plus y to the n equals z to the n for n greater than 2, this has no non-trivial, right? No non-zero solutions. No solutions where, it can't have at least one of x, y, and z be 0. But this is not the only consequence of modularity, and I want to really emphasize that it's a connection between two different worlds, and so you can use it you can have a hard problem in one area and kind of try to pass it through this connection, and then that maybe it can be solved. And you can pass it the other way as well. So it's kind of a bridge that you can cross either way. So there's this kind of Diophantine application. There's proving something called the Hasse-Weil conjecture for the elliptic curve. So maybe you've heard of the Riemann zeta function. You can construct certain analytic functions called L functions that are attached to algebraic varieties, for example, to elliptic curves. And the Hasse-Weil conjecture says that the L function attached to an elliptic curve has analytic continuation to the whole of the complex plane. So it has to do with certain kind of functions that are similar to the Riemann zeta function, these L functions of elliptic curves, and it has to do with proving that they have analytic continuation. And that's very hard to do if you start with an elliptic curve, but it's less hard to do if you start with a modular form because that already has a more analytic nature. And so the proof of modularity led to a resolution of this conjecture as well. And then this conjecture itself is needed to formulate one of the famous outstanding problems connected to number theory, which is the Birch-Swinnerton-Dyer conjecture. This is needed to formulate BSD precisely. This has to do with kind of the number of poles of the L function of the elliptic curve at a point that's not a priori known to be in the kind of range where the function is analytic. So you need to know that you have analytic continuation there. And it's also useful as an input for BSD in cases that we know in rank 0 and 1. And I don't know so much about this, but I wanted to mention it, that kind of starting out with an elliptic curve that you know is modular is, one of the main ways in which we've been able to make progress on this famous conjecture, the Birch-Swinnerton-Dyer conjecture. Okay, and so maybe I want to end with what is known about modularity now, which is, almost 30 years after this theorem was proved. And one thing, there's various ways in which you can try to generalize this theorem. And two very obvious ones are, you can try to change the field of definition of the elliptic curve. So you can look at an elliptic curve over an extension of Q rather than over Q itself. Or you can look at kind of a higher dimensional algebraic variety instead of an elliptic curve. So kind of the next step would be, for instance, to look at something of dimension 2. Those are called abelian surfaces. And so first of all, if F, and I want to restrict to the case, simplest case, where you go to a quadratic extension of the rational numbers, that can be, e.g., F is real quadratic. So this is the one where you take square root of some positive square-free integer. And then it's known that all E over F are modular. And this is a theorem from 10 years ago due to Freitas, Lehong, and Zixek. And they had to do a lot of innovative new stuff to prove this theorem over a real quadratic field. But at least some of the things in there, like the kind of the construction of Galois representation attached to the corresponding objects, the Hilbert modular forms that show up there, that was similar. So kind of the spaces that they had to look at were kind of like products of the upper half plane, H times H, rather than just one copy. But then there's also certain cases where F is imaginary quadratic. So for example, well, let me say it like this. So first, an imaginary quadratic, it's a quadratic extension of Q, where again, you look at a positive square-free integer, but now you adjoin square root of minus d. And here, our results are weaker, but here we know kind of that 100% of elliptic curves over F are modular. And in certain cases, we know all. And this is for example, for the field of Gaussian numbers, Q adjoined square root of minus 1, Q adjoined I. And this is a theorem that I proved in joint work with James Newton. So maybe let me put, this was 2013, and this was 2023. And so, there's been progress on modularity in the past 30 years, but in some sense, it's been quite slow. So even just going from Q to a quadratic extension has taken a long time. And I guess I also mentioned another generalization is you could go from E over Q to A over Q, which is an abelian surface. And there are some announced results of Boxer, Caligari, G, and Piloni. So they prove potential modularity of all of them. And they're proving new modularity, new cases of modularity, but their paper isn't out yet, so I don't want to state something precise. But just to give you a sense for, you start out with these reciprocity laws, and then, 30 years later, kind of this is the amount of progress that's been made in this kind of specific kind of connecting elliptic curves or higher dimensional generalizations to generalizations of modular forms. And it seems like even going from the dimension 2 case to dimension 3, that seems kind of hopeless today, or like one really needs some very serious new ideas before one could, go beyond dimension 2. But so it's a very active field. There's a lot going on in it. For the rest of the lecture course, what I'll do is really focus on modular curves and their geometry and some of the geometric results that were needed specifically for the proof of this theorem in the imaginary quadratic case. I'm done. Thanks very much for your attention.
Are there any questions?
When you define the square you took the state model, right?
The tape module, yeah.
Right, you took the P.
Yes.
Like, does it matter which P?
That's a good question. So in fact, in some sense it doesn't, because what you really have is not just one Galois representation, but you have a whole compatible system of Galois representations where P varies. And so you can pick, any P. And if you know that this relationship holds for one prime, then you can deduce it holds for another as well. And in fact, that's some version of this shows up as a key step in the proof of this modularity theorem, where you kind of switch between primes.
So the rho E takes account of all P kind of.
So, right, when I wrote it here, I could write rho E sub P, isomorphic to rho F sub P. And I could say this is true for every P.
Is the dependency of F on P just like which gamma 0 of retake, or is there something?
No, so the 11 is kind of fixed. So the F lives on a certain space, and you can't change the space that F lives on. But you can kind of change the prime P with which you probe it. So when you take a Tull cohomology, you kind of take it with coefficients in a p-adic field, and you can vary that P. So if we had a cohomology theory that gave us Galois representations and that had rational coefficients, then we wouldn't have to do that, but we don't have that. Yes.
In your theorem with Newton, is the certain cases like class number 1 cases? Or is it
No, it has to do with, you look at the elliptic curve x naught 15, which is something of rank 0 over Q. So it has finitely many points. And then when you base change it to imaginary quadratic fields, if it still has rank 0, then you know the theorem. And if it doesn't, then you don't. Then you miss some families of points.
okay.
Okay, we'll stop for now. If you have more questions, of course, you can ask.
Yeah, definitely come ask me.
Thank you again.